Okay, so today we do start the background information for trig. And we want to start out talking about geometry and basics of geometry. We mentioned some of this last semester, that the most basic shape in geometry is that thing right there. It's just a location called a point. And we showed last semester how we constructed everything in geometry from that basic concept. So we take it, we pull it in a single direction, we drag it in a single direction, and we create that line segment, and length was equal to distance. Or we could take it and we drag it in a single direction and keep on going forever, and we'd get what is called a ray. And those are what we're going to focus on today, is a ray. An array is described with two things. So I'm going to look at that ray right there. First of all, to name a ray, you have to have 2 points. One point must be the starting point, which I'm going to call point A. And the other point just is somewhere on the ray. So let's say I have points B, B, and C. I can either call that ray AB or ray AC. Because B and C are both on the ray, so as long as I name the starting point, I can name any other point along that ray. Now, the properties of a ray are given off of our basic location grid. You can think of this as being like our directional compass rose, east, north, west, and south. East is 0 degrees. North is 90-degree direction, west is 180 degrees, and south is 270 degrees. And then 360 degrees is back at 0, or east again. That vector AB is described from its unique starting point. Notice the starting point is at the origin, or the center of that grid. It's described by a magnitude. Well, we're just going to assume it goes on forever, so we're not going to worry about that. But it's also described by a direction, and its direction is, basically that angle from 0 degrees. So let's say this is at 39 degrees is its direction. An angle is created when I have a ray, and I go back to that starting point, and I go in a different direction, a distinct direction. So from that same starting point, I go in a somewhat different direction, creating a second ray. This common starting point, of course, is called a vertex. And now we have two rays with that common vertex. The angle, let's say I put a second ray over here. And let's say that the direction of that second ray is 71 degrees. The angle, the size of the angle created by those two rays, this here, is the difference in their directions. So 71 degrees minus 39 degrees would give you, what, 32 degrees? So that's a 32 degree angle because there's 32 degrees difference in their directions. Does that make sense? Well, this system here was based on the old navigation system. People used to be pretty familiar with navigation and direction and stuff like that. Not so much anymore. So we've kind of adjusted our view of angles now so that to define an angle, we talk about if I start in one direction, I make a complete turn, how many degrees is that? (360 degrees), good. If I start in a direction and I turn completely back the other direction, how many degrees is that? 180. Or if I start in a direction and I turn, so I'm going at a square corner, how many degrees is that? 90 degrees. How did you get the 180 and the 90? Well, 180 was just half of the 360. There you go. And the 90 is 1/4. It's a fraction of a complete turn. And that's what we've kind of changed our definition of an angle is a fraction of 360 degrees anymore. So if we have an angle like this, if I tell you that that is 41 degrees, that is because it is 41 3/60ths of a complete turn. Okay, so anyway, let's look at some now relationships. We've talked about this relationship. Where we have two angles that add up to a straight line. So if this angle here is 72 degrees, what's this angle over here have to be? Well, a straight line is how many degrees? 180. So it's 180 minus 72. That has to be 108. Good. That is what we call supplementary angles. They add up to 180 degrees or a straight line. We could also have two angles that add up to a square corner. If this angle down here is 68 degrees, what's this one up here have to be? 22 degrees. Very good. 90 minus 68, which is 22 degrees. That is what we call complementary angles. If you are anything like me, I could remember those two words, but I always struggle to remember which one is which. And the way I remember it is 90 degrees is a right angle, and you get complements when you're right. These two principles, the way I drew these two, are drawn as what we call adjacent angles. Adjacent angles are formed, if we go back to that idea of a vertex, or that common point that we're dragging to make a ray, we drag it a second time in a different direction to make an angle. Well, if we go back to that same starting point and we drag it in a third direction, we've created adjacent angles. Adjacent angles have a common vertex and they share a side. So this angle here, let's name these. Let's call this point A, B, C, and D. So if I wanted to name this angle right here, I could name it angle BAC. Notice the vertex must be the middle point, and then the other two must be 1 point from each side. So I could call this BAC or CAB, it wouldn't matter. I have to name, like I said, the middle letter has to be the vertex, and the other two letters, one has to come from one side, the one has to come from the other side. So this angle here would be angle CAD or DAC. And then there's a third angle, which is well more than three, but we got this one here, which would be angle BAD. There's also, of course, angles over here, but we're not going to worry about those. When we have adjacent angles, as we saw with our complementary and supplementary, we can do operations with those angles. They're additive and subtractive. For example, let's say that I tell you that BAC up here is 37 degrees and CAD is 79 degrees. I can then find angle BAD, that should be, sorry. Angle BAD by just adding. 79 plus 37 is 116 degrees. So when they are adjacent like that, they are additive or subtractive. If I gave you BAD, I could subtract one to the other to get the smaller angles. We can go a step further and deal with intersecting lines like this. If I give you that this angle here is 37 degrees, what can you tell me about this angle right here? That, of course, is a straight line, right? So the 37 degrees and then our angle marked in brown form a straight line, which means they are supplementary. Which means this angle must be 180 degrees minus 37, or 143 degrees. What can we then say about this angle here? Well, we know that this is a straight line, so that our angle marked in red, along with our 143 degrees here, forms a straight line, add up to a straight line. So again, that's 180 minus the 143, subtracts to give us 37. This must be 37 degrees. And without having to do any subtraction, what's this angle going to have to be? 143, good. When two lines intersect, it only forms two angles. The angles created are either supplementary or they are equal. The equal angles are what we call vertical angles. So here we have the 37 degree angles. Those are vertical. They are created on opposite corners, opposite sides of intersecting lines. The 143 degree angles are also a pair of vertical angles. Again, they're opposite corners of intersecting lines. So when two angles intersect, they will always either form, the angles formed will either be equal or supplementary. So these two lines here are called parallel. Now, a lot of us are used to the definition of parallel being parallel lines or lines that never intersect. And that definition sort of works when we're on a flat piece of paper or on a flat surface. In plane geometry, parallel lines don't intersect. But that's not enough if we're dealing three-dimensional geometry. For example, let's say I have, we'll just red ones so they show up. My two pens here. Right now, do they intersect? No, they don't intersect, but are they parallel? No, they're not. So in three dimensions, saying that they don't intersect is not enough. So the definition of parallel is always the same distance apart. So parallel lines are always the same distance apart. The technical definition is everywhere equidistant. It's just a fancy way of saying always the same distance apart. So if we have parallel lines and we cut across them with a third line, that third line is what is called a transversal. If I tell you that this angle here is 51 degrees, Well, I know a lot now about 3 other angles here. What do I know about this angle here? What's that have to be? 51, because those 2 are vertical angles. How about this angle here? 180 minus 51, or 129 degrees. How about this one? 129. So we know that all 4 of those angles are either equal or supplementary to that original angle that we found. How about the angles down here? Well, I can take this and slide it up, and it's going to lay exactly on top of that one, isn't it? And those angles are going to be exactly the same, aren't they? So this angle here would be the same as what? 51. And of course this one, also 51. This one here is going to be 129. And of course this one is also 129. When you talk about parallel lines cut by a transversal, if this were a formal geometry class, we would talk about corresponding angles, interior angles, exterior angles, alternate interior angles, alternate exterior angles, corresponding interior angles, corresponding exterior angles, blah, 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 blah. Alternate interior angles are congruent or equal. Corresponding interior angles are supplementary, and all those different rules. For our purposes, the same as like we said with intersecting lines. When parallel lines are cut with a transversal, all angles formed are either equal or supplementary. I don't really care you memorizing interior angles, exterior angles, alternate angles. Don't really care for you to have to memorize that type of vocabulary. It's not terribly useful.
Just go back up.
Sure, which one? Like these? Supplementary and complementary?
Yes.
Okay. Okay, so our next step. We've mentioned measuring these angles in 2 different ways, by the difference in direction and by the fraction of rotation. But I've been keeping the numbers nice and round so far. Let's have an angle here that is 32.57 degrees. Some applications, it's just fine to have it as 32.57 degrees. But we do have degrees get broken down into smaller units. 1 degree gets broken down into 60 minutes. The symbol for minutes is a single quote. Looks a lot like the foot symbol. 1 minute gets broken down into 60 seconds. The abbreviation for seconds is a double quote, just like the inch symbol. So it can be kind of confusing. You just have to go off the context. And if you see something like this, you know that's not feet and inches, because you'd never have 29 inches listed, would you? So you know that must be minutes and seconds for degrees. And realistically, very seldom do you have angles that are less than 1 degree. So at the very least, you'd have some sort of degrees up front most of the time. I mean, there are a few times where you have very, very small adjustments to surfaces where you'll have changes in an angle of less than a degree. Very seldom. So I have 32.57 degrees. That is what we refer to as decimal degrees. I want to convert to degrees minutes and seconds. What we refer to as DMS notation. So 32.57 degrees. The 32 is degrees. So I'm just going to keep the 32 degrees. Now I have to take the 0.57 and I have to convert it. Well, 1 degree is equal to 60 minutes. So you can see here, the degrees cancel out. It's 0.57 times 60. Gives me 34.2. So that's 34.2 minutes. So I'm going to take the 34 off. That's my minutes. And now I have the 0.2 minutes I need to convert into seconds. Well, 1 minute is 60 seconds. So 0.2 times 60 is 12 seconds. So that's 32 degrees, 34 minutes, and 12 seconds when we convert.
I don't understand why they use minutes and seconds.
The reasoning came about because of the clock and moving around the clock. A minute was a fraction of a clock, but a minute is a 60th of a rotation, but it becomes a 60th of a degree. So I never understood why they made that connection like that. I do know it all comes down to a clock, and that's one of the reasons why there's 60 minutes. It came from the Phoenicians were fascinated with the number 60 and 360. That's why 360 degrees is a complete circle. And the reason they were fascinated with the number 360 is because 360 can be divided by like nearly anything. 2, 3, 4, 5. It does not divide by 7, but 6, 8, 9, 10, 12. I mean, it can be divided by so many different numbers. So that's why they were fascinated with 360, and they made that there. 60 is kind of like a baby version of 360. It's divisible by a lot of things, not quite as much as 360. So that's why they did 60 minutes in an hour and 60 seconds in a minute. But yeah, there's a lot of it that doesn't necessarily kind of fit. I agree with that. We're going to do we're going to do a couple more examples yet. So let's say we have 71.38 degrees. Of course, this is decimal degrees, and I want to convert it from, I'll put this in abbreviations here, convert Yep, I'm going to show you that in just a few minutes. From decimal degrees to DMS. That's the button you'd be looking for on your calculator, by the way, DD to DMS. Yep. When you enter yours, depending on your calculator, the Casio actually has a button there, and the Texas Instruments, you have to go through a menu to get to it. So we got 71.38. We're going to take off the 71 degrees. We've got 0.38 left. So you put it over 1. 1 degree is 60 seconds. So you got 0.38 times 60. Gives us 22.8 seconds. So we got 22 seconds. And we got the 0.8 left, the decimal. 0.8 over 1. That's in minutes, so 1 minute, 60 seconds. So 0.8 times 60 is 48 seconds. So this is 71 degrees, 22 minutes and 48 seconds. So on your calculator, you would enter 71.38, and you could just leave it as that. Now, depending on whether you have the Casio or the Texas Instruments, if you have the Texas Instruments, you have a angle key up there that you would press. And in that angle key, you've got degrees, minutes, seconds, and you've got PRP, I believe, and then DMS. I should say be like an arrow DMS or whatever. So you arrow over to DMS. So you type in the 71.38, you hit that key and you arrow over the DMS. You're probably going to have to hit equals twice. And it should give you 71 degrees, 22 minutes, 48 seconds. Now, on the Casios and the Sharps, they all work just a little bit differently. So, find what you have for a key. I know on a lot of the Casios, you have a degrees, minute, second key that looks like that you would use for a lot of that. Is there anybody that hasn't been able to get their calculator to do it? Of course isn't. Okay. So I'm going to have you convert this one on your calculator quick. 18.793 degrees. Convert that to DMS, degrees, minutes, seconds. 18 degrees. How many minutes? 47? 34.8 seconds. So, yes, it is possible to have a decimal in your seconds. We never go past one decimal place in the seconds. So even if that's 34.8175, whatever, we stop there. We never go past one decimal place in the seconds. Up or down, depending on where it's at. Like if that was 34, that might be 34.79, who knows? And they just rounded it to 8. So now going the other way, if we have degrees, minutes, seconds. Let's say we have 35 degrees, 17 minutes, 54 seconds. And I want to take it, convert it from degrees, minutes, seconds into decimal degrees. Most of you on your calculator, and I'm going to do this example manually here. You would start with the seconds. We're going to convert those into minutes by dividing by 60. 54 divided by 60 is 0.9. So now I'm going to combine the 0.9 with the 17. I now have 17.9 minutes. Now I take my 17.9 and I divide by 60. Which is going to give me 0.298333333. To that I add my 35 degrees. So I have 35.2983333. Degrees. Does that make sense?
So can you just punch in your calculator?
On your calculator, the hard part is just getting it entered. If you have the Texas Instruments, you type in 35, you hit that angle key, and you select the degrees. You type in 17, hit your angle key, you select the minutes. You type in 54, hit your angle key, and select the seconds. Then just hit equals, and it should automatically flop to decimal degrees. On the Casio, you have that degrees, minutes, second key. You're just going to type in 35, hit that key. Type in 17, hit that key again. It's going to put another degree symbol there, but the calculator knows what that really means. Hit the 54 and hit that key again. Again, the calculator put another degree symbol there, but the calculator knows that that's seconds. Then just hit enter or equals, and it should flop it over to decimal degrees. So, we're going to look at doing operations with these angles, just like we did with other measurements. If I have 57 degrees, 18 minutes, 48 seconds. And I want to add to that 12 degrees, 37 minutes, 51 seconds. What value do I have to hit before I have to carry here? Well, how many seconds are there in a minute? 60. So I'll be carrying at 60. So 48 plus 51 is 99. So I'm over 60. So when I carry 1 up here into the minutes, what do I take away from the 99? 60 is what I take out. So it leaves me with 39 seconds here. I'm going to pause. Everybody see any questions where that 39 came from? I added the 48 and 51. I got 99. So I had to carry 1, which takes out 60. Now I've got 1 and 18 is 19, plus 37 is 56. That's just fine because it's not 60 or more. 57 and 12 is 69. That is my degrees, so there's nothing to carry there. Even though it is over 60, it doesn't matter. The degrees can be as big as it wants to be. So I want you guys to try. If I got 23 degrees, 39 minutes, 54 seconds, plus 18 degrees, 28 minutes, 42 seconds. And yes, you can enter that in your calculator. Just like you would enter degrees, minutes, and seconds before. You enter it in, you hit plus. Your calculator most likely, when you hit plus, will automatically convert it to decimal degrees. Then you'll type in the other one. When you hit enter, however, it's always going to give you the answer in decimal degrees. So you're going to have to convert it back in degrees, minutes, seconds. Yours gave it automatically in degrees, minutes, seconds? Cool. What'd you get?
42 degrees, 8 minutes, 36 seconds.
Perfect. Now, the one thing is that give it as 08 minutes or just 8 minutes on yours? Just 8. Okay. Some of them will give it as 08 minutes. So you've got to make sure you're careful with that. So just like you would enter 23, hit your degrees, minutes, seconds key. 39, hit your degrees, minutes, seconds key. 54, hit your degrees, minutes, seconds key. Then plus, then do the same to enter the 18, 28, 42. Then hit equals. Everybody get theirs to work? Like I said, many of you will have to convert it back to degrees, minutes, seconds because they'll give you the answer in decimal degrees. Or we might have 38 degrees, 27 minutes, 51 seconds. And we might subtract 12 degrees, 42 minutes, 18 seconds. When we subtract, just like adding, we move right to left. We're going to do 51 minus 18 is going to be 33. 27 minus 42 is an issue. What are we going to have to do? Borrow. So this becomes 7, 37. What do we have? What does the 27 become? It's 87. Why is it 87? Because 1 degree is 60 minutes. So when we borrowed 1 degree, it's 60 minutes we're adding to it. So 87 minus 42 is 45. 37 minus 12 is 25 degrees. So 25 degrees, 45 minutes, 33 seconds. And again, you can do that on your calculator. So try this one on your calculator, see if you can get it to work out before I get done with it. 22 degrees, 53 minutes, 26 seconds. Is that what you come up with? Yes? Oh, you're still doing the other one? Okay. Okay, so then we have to look at multiplication. So let's say we have 18 degrees, 27 minutes, 35 seconds. And we're going to multiply that by 4. Well, 35 times 4 is 140 seconds. Now, it takes 60 to carry. 60 comes out 140 twice. So it's 2 minutes. 2 times 60 is 120, so there's 20 left over. There's 20 seconds left over. So keep the 20 seconds here, and we're going to carry that 2 minutes. Now we multiply before we add. So we do 4 times 27 is 108, plus the 2 is 110. Well, that 110 again is going to be 160 with 50 left over. So there's still 50 minutes. We carried the 1 degree. 4 times 18 is 72, plus the 1 is 73. And that is just 73 degrees. So 73 degrees, 50 minutes, 20 seconds. Any questions? And again, you can enter that in your calculator exactly like we see it there. Enter the 18 degrees, 27 minutes, 35 seconds times 4, and it'll pop right out. Or we could have 57 degrees, 39 minutes, 24 seconds. And let's say I want to divide that into 6 equal pieces. Just like dividing our other measurements, we go left to right. It's the one operation that goes left to right. 6 goes into 57 how many times? 9? There we go. 9 times 6 is 54. That leaves us with 3 degrees. Now, just like we did with inches and feet and inches, before I bring down the 39, I have to take this 3 degrees and convert it into how many minutes? 3 times 60 is 180. Now I can bring down the 39, that's 219 minutes. So now 6 goes into 219. Well, 6 goes into 21, 3, carry the 3, 36 times, right? 36 times 6 is what? 216, I believe. Which leaves us with 3 again. Well, before I bring down the 24, what do I have to do with that 3? Times by 60. It's 180 seconds now. Bring down the 24 is now 204 seconds. 6 goes into 204. 34, I believe. So that's 9 minutes, or 9 degrees, 36 minutes, 34 seconds. Again, you can enter that in your calculator. Do the 57 degrees, 39 minutes, 24 seconds, and then divide by 6. And it should spit it out. Got a little bit long-winded on you guys today. In the packet I just passed out, page 266, 1 through 75, the odds. Deal with angles, adjacent angles, supplements, complements, and operations with our degrees, minutes, seconds. Make sure you do at least a few of the conversions in the operations of degrees, minutes, seconds, just to make sure you've got your calculator down. That's something you're going to have to get quick with, because we're going to do a lot of work with it. Okay, I'll let you have the last 5 minutes to get started.